Said, thank you.
Okay, thanks. All right, so thank you. So I'll talk about calorimetry in general, and I'll give basically an overview of different types of particle showers that can occur inside calorimeters, why calorimeters are used, and various manifestations of how we build calorimeters. So I think one thing to keep in mind is that the underlying physics that sort of exists inside calorimetry is pretty straightforward interactions between particles and matter, and we'll go through those. But those simple interactions can actually manifest themselves in quite complicated ways, and you can actually build quite a variety of devices to sort of deal with different situations. So, for example, on this slide, you can actually see different kinds of calorimeters that are in use or will be in use. So, for example, there's this on this side. There's this a 0-degree calorimeter that will be used at EPIC in the EIC, and it's basically a sampling calorimeter where you basically sample the produced shower at different positions along its creation after its creation. Then you have this lead tungstate homogeneous calorimeter that's used at CMS. And then you have this what's sometimes called a spaghetti calorimeter or a sci-fi calorimeter, where you run scintillating fibers into an absorber material and actually read out the light from those scintillating fibers. So we'll kind of discuss why you would use these different types of calorimeters. To start, let's talk about why calorimetry in general. And I think the sort of the most straightforward way to think about this is to ask the question, what do we actually want to measure for any given particle or collection of particles inside a detector? So we have particles that live long enough that they can actually stream into our detector and they can be measured. So these can be, say, electrons, positrons, muons, photons, charged pions, charged kaons, protons, neutrons, and kaons. So some of these things that we would want to measure is, of course, this four momentum vectors of these particles. So the energy and the momentum vector. We'd want to know what particle type it is. So we want to know if it's a positive pion, a negative pion, an electron, so forth. And we also want to know its creation point. So did the particle come from, say, a decay of some other particles? So, for example, is the particle from a decay of, say, a D0 meson, or is it from some initial sort of hard scattering? And so for the simplest thing you could think of to do would be, okay, you have a tracking detector that measures the momentum vector, and then you have a calorimeter that measures the energy. So can you just basically measure the energy in the calorimeter and measure the momentum vector in the tracking detector, use that to reconstruct the particle mass, and that's all you need to do? And that would be the first thought you could have, but that's something we can almost never do. And the reason for that is basically calorimeters and trackers have uncertainties on the order of a few percent at best. So you basically measure a momentum vector with some 1 to 10% uncertainty. Similar with calorimeter, you measure the energy to some similar level. So you can't really reconstruct the mass because you're kind of trying to subtract two large quantities to get a small quantity. So what you actually do is there's kind of two types of approaches. So you can think of one is a calorimeter-based reconstruction approach, in which case you would measure, you need some detector to tell you what the PID or the type of the particle is. So that might be a Cherenkov detector or a time of flight detector. And once you know what the type of particle is, then you can measure the energy in the calorimeter, and you can measure the momentum direction, not the magnitude of the momentum, with some tracking detector or with the calorimeter itself. and then you can form your 4-vector using the known mass of the identified particle. So the other method is to use sort of a tracking-based reconstruction, in which case you measure the momentum vector in the tracking detector, and then you use basically PID information from the dedicated PID detectors. And then the best approach for the highest precision is somehow to combine both of these information from both of these methods, or to use the calorimeter to even aid in this sort of PID needs. Okay, so yes.
Sorry, I apologize if you said this and I missed it, but can you go back?
Sure.
Why for the calorimeter, you have E and then, but then in the, I guess you're just saying that you measure you add up, so you have the P had, and I guess it's because when you reconstruct the trajectory and then sum up the entire energy, is that what you would that?
Yeah, so what the calorimeter, so if we want to get a 4-vector, say the energy and the momentum vector plus the particle ID type, so the calorimeters will give us, as we'll see, basically the total energy of the particle. Of course, then we also want them, if you know the total energy of the particle and you know the PID from some dedicated PID detector, say some Cherenkov detector, or time of flight detector, then you know the total momentum of each. Yeah. But we also want to know the components of the momentum. So that's why I just meant you need to get these components either from using where in the calorimeter the particle was hit, or if it's a charged particle, since it's turning in a magnetic field, you need some other information.
Thank you.
Yeah. Yeah.
So at the beginning of that slide, you say like you motivate this method because we know the masses of the particles really well. But what about the hadrons that we don't know the masses really well?
Right. So okay. So you might have something, say there's all these resonances, say F2 resonance or something. But the point of those is they will always they won't hit our detectors. So decay in some short. So our detectors, you can think on the order of centimeters or meters away from the interaction point. So those particles would decay, and then they would decay into 2 stable particles, which we will basically be able to, which we know the mass of and which we can detect. And then the interesting point for those is to actually reconstruct that, say 2 particles came from were created at the same point. And if that's the case, then you can reconstruct their total mass, and maybe it will be at a resonance, at a massive resonance.
What about the ones that have like very large widths?
Yeah, so I mean, it depends what you're trying to do. So for example, if you have a particle that that has a large width, you reconstruct the mass. The mass that you reconstruct in your detector will be a convolution of the decay width and your detector resolution, whichever method you choose. And then there'll be some background from, say, combinatorics, say particles from other parts of the collision combined with each other. And then you basically have to know your detector resolution. So you would see some peak, you would basically remove that detector resolution effect, and you can see your true basically decay with that particle. Does that make sense? Yeah. Okay, great. Okay, so let's just start with the basics of what are calorimeters. So calorimeters measure energy as well as position. So if they have some fine segmentation, you can know where that energy measurement is actually occurring, and you can get some information about the position of where the particle hit. But the main idea is we measure energy with calorimeters. And one thing about calorimeters is they make destructive measurements. And by destructive, I mean that the particle will not exist after the calorimeter makes that measurement. So you basically need to put your calorimeters outside the other detectors. So you need to put them outside tracking detectors, outside Cherenkov detectors, so that they will actually, because once they hit the calorimeters, the particles can't be seen by other detectors. And so the particle is fully absorbed. Now, an exception is muons, which actually can pass through a lot more material. Now, when the particle hits the calorimeter, it initiates something called a particle shower. This means that it creates secondary particles inside the detector volume, and then these particles get absorbed. So basically, the whole energy of that initial particle is converted into heat, which is why we have the name calorimeter. Now, in nuclear and particle physics, we do not actually measure the increase in temperature because, you know, one electron's not going to increase the temperature of a block of lead and scintillator to like an appreciable degree. But rather what we do is we measure excitation signals. So we measure basically ionization energy loss in scintillation material that's embedded in the calorimeter. And that's how we actually measure the energy. So the amount of the scintillation light we measure, the ionization we measure, is proportional to the energy of the particle. Okay, so why are calorimeters actually needed? So we discussed this a little bit, but the idea is calorimeters have some differences with compared to tracking detectors that basically make them complementary to tracking detectors. So one thing is that the calorimeter performance in the sense of its resolution, so how well it can actually measure the energy, actually gets better with increasing energy. So this is like shown by this blue curve here. While for a tracking detector, the performance actually tends to get worse with increasing energy. And this makes sense because if you have a fixed magnetic field in a tracking detector, you're basically a particle with higher momentums going to bend less. So you're going to be able to determine that circle of bending with less precision. Okay, so you have this sort of complementarity between the two detectors. And then for charged particles, in addition, even when you can measure the momentum better than you can the energy, you can still use both pieces of information to do particle identification. So for example, electrons will behave slightly different in calorimeters than hadrons. And the other thing is that calorimeters are the only way to detect neutral particles. So for example, photons, we can only detect, they won't leave any trace in a tracking detector, embedded in a magnetic field, but they will leave all their energy in a calorimeter. So we can measure them in the calorimeter. And this is very important, for example, for jet physics, where almost 30% of your jet energy goes into neutral pions, which decay almost instantaneously into photons. So you have to measure basically a lot of neutral particles to actually measure jets. And calorimeters can be arranged basically to have very good 4-pi coverage. So what I mean, you can basically cover a large, basically a large cross section, and you can, as I say, you can measure jets, which basically subtend a larger region of the detector, and you can also measure missing energy. So this is, for example, missing transverse energy. And one other feature of calorimeters is that as you increase the energy of the particle hitting the calorimeter, that shower will spread out in some distance longitudinally, but the longitudinal depth of the shower only grows with the log of the energy. So you can actually keep calorimeters to a reasonable size and measure a large range of energies. And then the last point is that energy deposited in calorimeters can be read out in a actually very short period of time, which is important for event triggering. So for example, at the LHC, we have basically bunch crossing, so proton-proton collisions, and they happen at something on the order of, I think, like 40 megahertz. So one bunch crossing every 25 nanoseconds. So you have to actually be able to kind of sort your calorimeter energy deposits into different collisions, and this requires you to read out the collisions in a short period of time. Okay, so let's start with electromagnetic calorimeters. So as I said, we basically just need to understand some of the simple features of the interactions of photons and electrons and positrons with matter to deal with electromagnetic calorimeters. And so the first thing is for photons, there's various processes that the photons can happen to photons when they interact with matter. So and these processes are energy dependent. So at lower energy, photons can either undergo the photoelectric effect or Compton scattering. Above 100 MeV, the dominant interaction of photons with matter is pair production. And as you can see, basically there's two types of pair production. There's this sort of what's called kappa E, which is the pair production in the field of the electrons surrounding the nucleus, but the majority of the pair production happens in the in the electromagnetic field of the nucleus. And you can also notice that this cross section tends to basically approach a fixed value above, say, a GeV. So what this actually means is that this cross section, so pair production is basically the dominant feature of the interaction of the photons with matter. And the important point here is that since this approaches a constant, we can actually characterize the cross section in terms of something we call the radiation length, which is a property of the medium that the photon's interacting with. So we actually say that this mean free path, lambda, which is basically the average distance for one interaction, one of these pair production interactions, basically is proportional to this radiation length. Okay, so basically the radiation length sets the scale of how often you're going to have this pair production or the photon splitting into an electron-positron pair. And then for electrons and positrons themselves, they can lose energy basically in two methods. So one is ionization energy loss, where they basically excite or ionize the electrons inside the nucleus of the medium, or you have this Bremsstrahlung production where they basically radiate photons in the electromagnetic field of the nucleus. And as you can see from this plot, basically, if you go, say, above, say, 100 MeV or even a little lower, depending on the medium, you basically, electrons and positrons basically lose almost all their energy through this Bremsstrahlung process, while having some small amount of ionization loss. And again, this cross-section tends to kind of saturate higher energies. So we can again characterize the energy loss of the cross-section in terms of this radiation length. And what we basically see here is that the energy of an electron will lose about 63% of its energy after one radiation length. Okay. So basically what's happening then in the shower is what's happening then in these calorimeters is the electrons comes in, or the photon comes in. If the electron comes in, it radiates off photons, which in turn pair produce additional electrons, and those pair produced electrons and positrons, they radiate additional photons. So this will so you get this expansion of basically an electromagnetic shower governed by this radiation length as the key parameter. Okay. So there's actually material dependencies to these cross sections. So basically, you can see that if you're for photons, the point at which pair production becomes the dominant feature basically changes a bit with the increasing Z of the material. Similarly, what we call the critical energy, which is the point at which the ionization curve and this radiation curve or Bremsstrahlung curve cross, that decreases with increasing Z of the medium. So in terms of actually having a signal from the calorimeter, something we can measure, the only thing that we actually have access to really is the ionization as well as Cherenkov energy losses of the electrons and positrons. So this green curve is actually the ionization loss, and that's what we're actually going to measure. But the shower development is going to be basically governed by this this sort of red curve and this yellow dash curve. Yes.
So that's, maybe you're gonna talk about this because, and you just said this, but is the idea that you pick the material which you're gonna measure the ionization, and you say, we know that at this end, like if we measured, I don't know, like 100 MeV photon, we expected that to be 70% of that is ionization energy, and the other rest is the radiation loss, or
Right. So I think there's 2 points. So one is that, so the energy, so basically the energy of any particle will be fully deposited in the calorimeter. Eventually, that energy is going to all deposit as ionization.
Okay.
So it keeps splitting until you get the end where basically it's below some threshold.
I
So
see.
once you get low enough energies, then you basically only lose energy through ionization.
Okay.
And the signal is going to be proportional to the energy loss of that, or the initial energy of that particle.
Okay, thank you.
Okay, and one thing that yeah, I think this is actually kind of to your question. So calorimeters are basically intended to measure GeV or TeV energy particles, but the performance is really determined by what happens on the lower energy level. So basically, if you actually look at the ionization energy that's deposited into the calorimeter, a lot of it is really coming from electrons at very low energy, so on the order of 1 to 4 MeV. And this is really basically where as you can see on this plot, where this green curve is larger, or is at lower energies. Okay, so you can actually develop a simple analytical model of a shower. And the idea here is that if you make the assumption that at the critical energy where the ionization energy loss and the radiative energy loss is equal, if you make the assumption that above that energy, there's no loss by ionization, and below that, there's only loss by ionization, so there's no more splitting. You can make some simple, you can actually learn a little bit about the main features of a calorimeter shower. So first off, you would basically have this splitting effect. So you would basically, after one radiation length, you would get 2 particles, then after 2 radiation lengths, 4 particles, and then so forth. And the energy would basically divide by a factor of 2 with for all the particles after that number of radiation lengths. So after a certain number of radiation lengths at SNOT, you would basically have 2 to the T particles, okay, after T radiation lengths. And then each particle would have this energy E over 2T, and the particle would stop if its energy went below the critical energy. So the total number of particles that you end up with is just the energy of the initial particle divided by the critical energy in that case. And the point this actually tells us, if you basically, okay, then you equate this 2T particles equal to E over EC, you get something that the maximum of the shower, your shower, where the point where you have the most number of shower particles will grow as log of the energy divided by the critical energy. So what this actually shows is that basically the longitudinal shower distribution increases only logarithmically with the primary energy of the incident particle. So for electromagnetic calorimeters, at least, they can be fairly compact. So for example, if you had, so we look at, say, for some, steel, you might have a critical energy of something like 10 MeV. So if you have a 1 GeV particle, basically you can contain that in about 4.5 radiation lengths. For a 100 GeV particle, you can contain it in about 9 radiation lengths. So that means a 100 GeV particle can be contained in, basically taking this number here times this number here. A 100 GeV particle contained in about 15 to 16 centimeters of iron or 5 centimeters of lead. Okay, so you can make these fairly compact. And then what about how the energy is deposited as a function of distance? So here what we have is, this is basically a parameterization that has some physics motivation and is also based on some fits to the data. But basically the idea is the energy lost per, say, so this is, you can think of this as the depth inside the calorimeter in units of radiation length. And then this is basically the energy lost per unit radiation length. And you can see that, okay, as you increase the the energy of the particle, the area on the curve obviously increases, so that this area is equal to this or proportional to this an incident energy, but the maximum shifts gradually towards the right. And that's captured by this this parameterization. Okay, and one important difference is actually, in practical terms, is actually that there's a difference between showers induced by charged particles, electrons and positrons, versus showers induced by photons. So you can actually see that for electrons and positrons, basically they tend to lose more energy at earlier stages because they actually start to Bremsstrahl or radiate immediately when they enter the calorimeter, while a photon usually takes something on the order of 1 radiation length before it actually pair produces. So this difference is actually sometimes useful in pre-shower detectors to actually distinguish electrons from photons. Okay, so this shows just as a function. So say for some I think for copper, if you throw different energy particles in the copper, how the energy is deposited as a function of the depth. And this is just all these curves are normalized to the same area in this case, but you can see how the peak grows gradually as you increase the energy. So basically, in this case, you're increasing the energy by law, this is increasing by orders of magnitude, and you can see how the peak position is actually basically changing linearly in that case. Okay, so one interesting thing is after you reach the shower maximum, the shower tends to decay, and that decay actually happens a little bit more slowly. So even though the peak is actually growing, the peak is governed by their this logarithm, it goes as the log of the energy. The decay of the shower following the peak actually has a much longer tail, and that tail is actually governed by ionization and Compton scattering. So basically, as the photons get to lower and lower energies, they tend to Compton scatter and even undergo photoelectric absorption, while the electrons tend to basically just lose energy now more through ionization rather than radiation. And this basically shows that, yeah, showers are really shouldn't just be thought of as a collection of minimum ionizing particles. They really have this more complex feature towards towards the end of the shower. Okay, so in terms of the lateral, so that was on terms of the longitudinal profile. So in terms of the lateral profile, the transverse size of a shower, so even if you throw a particle, say, at a block of material, that shower is not going to be at one point. It's going to spread out a little bit in, say, in the transverse plane. And that transverse shower size is governed by 3 things. One is the typical angle of Bremsstrahl and emission at high energies. Second is multiple scattering at lower energies, and the other is the propagation of the photons. So once the photons have some angle from the Bremsstrahl, they will propagate some distance before pair producing. So the main contribution is actually number 2, the low energy electron basically scattering or what's called multiple scattering or Moliere scattering. And the important feature here is that this this transverse size of the shower is basically governed by something we call the Moliere radius, which is again a function of the radiation length, but also a function of this critical energy. And you can see in these curves what this is showing is if you take a 50 GeV electron and you put it into a block of basically this like tungstate crystal, this is how the energy profile looks as a function of longitudinal distance. So as we change our longitudinal distance into the shower, this is how the lateral profile looks. So basically what you can see is that most of the shower gets contained in 2 or 3 Moliere radii. But also as you go farther into the shower tends to spread out more and more laterally, which makes sense because the shower is starting, say, at a point, and then there's a general spread in the transverse direction. And you can kind of see this in this three-dimensional, or this sort of sketch, which shows both the longitudinal development and the lateral development simultaneously. So you can see as you go farther and farther, the shower tends to spread out more laterally. But I think for electromagnetic calorimeters, there's some useful equations that you can use for quick calculations. So basically, you can see that how the radiation length will depend on the material, how the critical energy will depend on the Z of the material, how your shower maximum in terms of radiation lengths will also depend on your shower energy, on your particle energy and the critical energy, and how big you need to make your calorimeter to actually contain, say, some fraction of the energy. So there's always, in real experiments, you may not always have room to make your calorimeter as big as you need, so there'll be some leakage. But you can see how wide you need and how long you need to make it in order to, for example, get 95% containment. Okay, so are there any questions there? Yes.
So the EM calorimeter is inside the magnetic field, right?
It doesn't have to be. It can be. Many times it will be. Yes.
So the charged particles will curve in the scintillators, right?
So if the calorimeter is inside the magnetic field, there's a magnetic field effect. But the point to make here is that, as I said, if you have this 100 GeV electron and it hits so it's curving before it hits the calorimeter. Once it hits the calorimeter, it will be absorbed in something on the order of tens of centimeters. So it's really not something where you have to think about that. Yeah.
Thank you.
Okay, so then, so what about muons? So as I mentioned, muons tend to actually be very penetrating particles. And one thing you can see is this critical energy of the muons compared to the critical energy of the electrons. So where the radiation loss and ionization loss are equivalent, that's basically sort of 10 to the 4 times larger for muons than for electrons. So muons would tend to lose energy through ionization, and for a large range, they're somewhere close to what we call minimum ionizing particles. So they're basically at this valley of energy loss for ionization. So that's shown kind of here on this plot. So this is, I think, for some TPC or some time projection chamber, how different particle species sort of energy depends on their momentum. And there's this minimum here, which is called the minimum ionizing peak or minimum ionizing particle energy loss. And muons, though, are not quite MIPS. They actually do have some radiative losses. So, for example, even if you're for example, in a lead calorimeter, the critical energy for muons is 250 GeV. So for some of these larger energy muons, they will actually be farther along this curve. So they'll have both ionization and radiative losses. But I think the important point is that muons are quite penetrating, and they will lose the energy primarily through ionization and won't induce really a shower. Okay, so what's important for actually measuring the shower? So there's 2 things. So the first thing is linearity. So we want our signal to basically grow. So our signal is something that we'll measure. So basically that could be the number of say photons from scintillation. It could be some charge that we measure in some semiconductor detector that's attached to the calorimeter, or it can be some Cherenkov light. But in any case, the signal should be proportional to the energy response, and that's the way we can actually use that signal to measure the energy. So if we know that our signal is proportional to the energy, or this response is flat, then we can say, okay, if I measured this signal, then I can basically calculate an energy that was deposited. Because we don't actually know in the experiment, we don't know what energy the particle has. We need to use the signal to recover the energy. So a linear calorimeter has this constant response, which is basically the signal the average signal per unit deposited energy. And in general, electromagnetic calorimeters are linear with some caveats. And hadronic calorimeters, as we'll see later, are nonlinear due to something called non-compensation. So sources of nonlinearity for electromagnetic calorimeters include instrumental effects. So for example, if your light collection device saturates, there's too many photons hitting it, or if the response varies with something that varies with energy. What I mean by that is if there's differences in your signal depending on whether energy is deposited, say, towards the back of your calorimeter compared to the front of your calorimeter, or if there's leakage, then you will get some nonlinearity. So what we usually do is we characterize the other feature that's important for the shower measurements, which is fluctuations in terms of a couple different uncertainties that we basically divide. So there's various types of uncertainty. So one is what we call the sampling fluctuations, or this stochastic term. So that just has to do with the fact of how many particles are actually produced in the shower. So we produce n particles in the shower. There's a Poisson statistics effectively, which goes like square root of n. So that's basically leads to this basically this term, the C2 term here, which is basically tells us that the fractional energy resolution of the calorimeter will improve as 1 over the square root of E. So that's usually considered the main term in the calorimeter at moderate energies. But then there's two other terms. There's a constant term, which deals with this constant term, say C1 here, which can encompass several things, but it can be due to the inhomogeneities in the readout or the actual hardware. It can be due to other imperfections. It can be due to nonlinearities that I mentioned, or it can be due to calibration issues, actually trying to get that calibration from signal to energy and that not being perfect. And then there's a noise term, which actually due to say readout electronics. But that tends to be rather small. So this last term here is actually somewhat small. So a lot of times you can describe the energy resolution in terms of a constant term plus this stochastic term, which is this term that actually improves with energy. Okay, and then calorimeter types. So for EM cals, there's basically two types, and actually this is there's basically two types for EM calorimeters. For hadronic calorimeters, there's only sampling calorimeters, but we have what we call homogeneous calorimeters, which in which you have a signal, one medium which serves both as the absorber. By absorber, I mean the thing that actually say generates the shower, and the detector, or the active region. So for example, you can have things like scintillating crystals, which basically have small enough radiation lengths that they will generate a shower, but you also produce scintillating light. You can also have things like lead-loaded glass. So that's like lead glass, which will produce showers, but also shrink of light, which can be detected. And the idea is whenever you produce these showers, you need some kind of detector in the back. You say a light detector that will actually detect the amount of light that was produced, or be proportional, detect the amount of light that's proportional to the amount of light that's produced. And then you can also have these sampling calorimeters. And the idea is you can think of these as like a sandwich, where basically you have alternating layers of absorber material, which can be lead or steel or copper, basically what we were talking about before. And those alternate with active detector layers, such as silicon or some kind of scintillator or some liquid argon. And then the tricky part is actually how to best get the signals out of these, the light that's deposited in these active layers, how to actually get those out and actually get them into a photo sensor. So let's first look at, so I'll talk a little bit about that, but let's first look at homogeneous calorimeters. So the idea here, as I said, one block of material serves as both the absorber and the active medium at the same time. So one example of this is lead tungstate. So these lead tungstate crystals were used, for example, at CMS, and they're optimized for very good energy measurements. So, for example, they were used for the Higgs to gamma measurements. And the advantages of these homogeneous calorimeters is that they see all the charged particles in the shower. So they don't sample the shower, they actually see everything. And then they have the same response basically everywhere. But the disadvantages are they tend to be quite costly if you have to instrument a large volume, and they have limited segmentation. So basically the crystals, you can only make them down to a certain transverse size. So in these crystals, for example, at CMS, they were made basically the length. The length is about, this is about, I think, 20 centimeters or maybe 50 centimeters, and these X and Y sizes are about 2 centimeters, so on the order of the Moliere radius. And then other examples are if you go to actually low energy detectors. So, for example, at FRIB, gamma, if you do gamma spectroscopy, people will use semiconductor crystals such as germanium for MEV level gamma spectroscopy, and there you can actually measure very good energy resolutions for MEV particles. But you can't really use these semiconductor. You cannot use these semiconductor crystals at higher energies, even though the stochastic term would improve. The reason you can't use them at high energy colliders is they really are very sensitive to radiation damage. They have limited lengths, and they're slow. You can only read them out quite slowly. Okay, so what about sampling calorimeters? So as I said, they use both passive and absorber material, passive material, which is the absorber material, and the active material. So the idea here is you interleave some high density absorber with some active readout devices. So most used are what we call sandwich structures, but you also can have embedded scintillating fibers. And then we define something called the sampling fraction, which is the ratio of the energy deposited into the active material compared to the total energy deposited. So that's the total energy of the particle. So maybe, a sampling calorimeter, and maybe we'll see 5% of the energy. So 5% of the energy will be deposited into the blue layers, while 95% will be into the absorber layers. So they can be basically, you can make these fairly cheaply, and they can have both transverse and longitudinal segmentation. So you can, in principle, read out information from each one of those blue layers individually. And then the disadvantage is basically, since you only see part of the showers, you have worse resolution. Okay, and actually, interestingly, this sort of sandwich type calorimeter is referred to as shashlik calorimeters, which comes from the, I think, Russian word for coupons. And then for the embedded fiber calorimeters, they're sometimes called spackle calorimeters, which are spaghetti calorimeters. So you have some interesting names. So how do you actually read out the calorimeter signals? So basically the idea is you need some kind of light collection device, or some kind of ionization, some electronic, something that's sensitive to, say, ionization loss. So I think for all of these examples, we have basically, we're thinking about creating scintillator light. And one way to do it, so for example, if you had this sampling calorimeter, one thing you could do is for each of these layers, you basically, that produce scintillating light, you attach a wavelength shifting plate, and that basically guides the light into a photodetector. And then your photodetector can be a PMT, or more recently, what we call a silicon photomultiplier. So these silicon photomultipliers basically act very similarly to PMTs, and they basically detect whenever you get a photon, there's a finite chance that you will actually give a signal out. And basically the total signal is the sum is proportional to the number of photons that hit that psi PM. And as you can see, there's various ways to instrument this detector. You can use sort of this thing where you embed the psi PMs inside the detector and get very nice longitudinal and transverse segmentation, or you can do more of a standard approach where you basically just read out everything at the back of the calorimeter, for example. Okay, so what determines calorimeter resolution? So in the homogeneous calorimeters, I think the most important thing to keep in mind is the idea is that there's some energy required to produce some quanta of material some signal quanta. So for example, in silicon detectors, you need 3.6 electron volts of energy to create an electron hole pair. So basically your number of particles that you are going to produce, which can contribute to the signal, is basically equal to total the energy that you of your particle divided by this energy to produce a signal quanta. And so then basically you get this N here is what's going to determine your counting statistics. So at high energy colliders, resolutions can be on the order of 1 to 3% stochastic, so per GeV. So I write it at 1 to 3% divided by the energy in GeV. So at 1 GeV, you have basically 1 to 3% energy. And then for sampling calorimeters, there's basically two things that matter. One is how often you sample the shower. So basically how many samplings you have. So how many of these layers of alternating absorber and active material you have. And then the second thing is your sampling fraction. So a larger sampling fraction will give you better resolution. So overall, you get something on the order of, say, 10% stochastic terms for sampling calorimeters. So basically an order of magnitude worse. Okay, so let me show some examples of EM calorimeters before I talk about hadronic calorimeter. So an example is in the Phoenix detector. So this was a detector that was operated at Brook until I think 2016. And they had two types of calorimeters. So they had this lead scintillator calorimeter. So it was a Shashlik type, alternating layers of lead and scintillator plates. And then what they actually did was they ran wavelength shifting fibers basically through the calorimeters. And they used that to pick up light that was created in the scintillating plates. And then they ran those wavelength shifting fibers to the back where they were attached to photomultiplier tubes. Then they had this a homogeneous calorimeter, which was a lead glass calorimeter. And what they did there, so that was in these two sectors, they had this lead glass. And there the light is a homogeneous calorimeter. So the lead glass produces the shower, and it also allows the electrons to produce Cherenkov radiation, which was read out by a photodetector at the back. Okay. Yes.
Why did they? How bad was the top cap? Like where I guess it's like the bulk of for the central magnet. Didn't like. I guess I naively expected to be.
Yeah. You mean why this is not like a 4 pi detector?
Yeah.
Yeah. So I think so. It's partly because at Brook they had these they had multiple detectors. One was Star, which is more like a 4 pi detector. This Phoenix was well designed for detecting electromagnetic probes.
Oh.
So they were looking for a certain kind of physics that basically allowed them to build sort of very high sort of resolution detectors for electromagnetic probes in certain acceptances.
All right, thank you.
Okay, then another example of homogeneous calorimeters are this sort of lead glass. This lead scintillator, lead tungsten scintillator, and this is used at CMS. And you can see this is roughly the resolution they get, so something on the order of 3% a stochastic term. And this is actually quite much better than, for example, what they have at Atlas, where they use sampling EM calorimeter. And then at SPhoenix, which is an experiment again running at RIC currently, they use the sci-fi style calorimeter. So what they do here is they basically embed scintillating fibers into a tungsten powder array. So they basically have a mesh of say some epoxy. They embed the scintillating fibers and then they pour tungsten powder over it. So their active area is the scintillating fibers, which collect the light and transport them to the side PMs at the back. But they also, and the absorber material is this tungsten powder. Okay, so here's just a summary table for eCal. So you basically have some, as you said, there's these homogeneous calorimeters, which can have energy resolutions on the order of a few percent. And then there's these sampling calorimeters, which can have energy resolutions with stochastic terms on the order of something like 10%. Okay, so one important consideration before I turn to hadronic calorimeters are that, EM showers are not just a collection of MIPS, as I said. So the sampling fraction can actually change a bit as a function of the shower depth. And this can happen especially in very high Z materials. So this isn't a big issue if you don't have any longitudinal segmentation. So you just read out your calorimeter at the back. But if you actually have longitudinal segmentation, this is actually an important feature that you need to take into account. And it can actually be quite tricky to intercalibrate different sections of a longitudinally segmented calorimeter. And this is actually important if you actually go on to work on future calorimeters, many of which will actually have this kind of longitudinal segmentation. Okay, so I'll talk a little about hadronic calorimeters, maybe for 15 minutes or so. So for hadronic showers, so for hadronic particles, they create what we call hadronic showers, but there's an extra complication compared to photons or electrons, and that's, of course, these hadronic showers these hadronic particles can interact with material through the strong interaction. So a hadron that undergoes a nuclear reaction will create a number of secondary particles, and these particles will then go on and undergo additional nuclear interactions, which forms what we call a hadronic cascade or hadronic shower. It will actually, some of those particles produced in the nuclear interactions will be neutral pions, and as well as atom mesons, but primarily neutral pions, and those will decay instantly into 2 photons. And those photons will then create electromagnetic showers. And then part of the initial energy of the hadron goes into initial energy of the incoming hadron goes into actually breaking the nuclei. So that actually leads to what we call invisible energy. So this is invisible energy, that is energy used to basically deal with the binding energy effect or breaking the nuclear binding energy. And this invisible energy cannot contribute to the signal. And then for hadronic showers, the governing length scale is what's called the hadronic interaction length. So how do hadronic showers actually, or how do hadronic interactions actually look? So you can think of it basically like this. If you have an incoming hadron, if it's charged, it will lose some energy through ionization loss. And then after going through one nuclear interaction length, it will basically interact. It will do a hard scattering with say a nucleon inside the nucleus. That hard scattering will produce some hadrons, which basically can go on to actually have a nuclear reaction with additional nuclei. In addition, it can produce a pi zero, a neutral pion, which can decay, and then those decay photons can also create electromagnetic interactions. And then in addition, after this, the nucleus will be left in an excited state. And that excited nucleus can either evaporate or fission, which will produce either produce some neutrons and light charged particles or produce some medium mass particles. So there can be a lot of different particles produced and various stages to the interaction. So basically the general features are that particle multiplicity will scale with energy and with the particle type. For incident charged pions, about a third of the shower particles will be neutral pions, and these will be produced through the charge exchange process. If this charge exchange process occurs in the first nuclear reaction, most of the energy of that pion will actually be deposited through EM showers rather than hadron showers. And then there's something called a leading particle effect, which is that fewer neutral pions are produced in proton-induced showers compared to pion-induced showers. And this is a result of the fact that when initially the initial nuclear reaction cannot produce a neutral pion because there can't be a charge exchange for the reaction in order to conserve baryon number. Okay, so as you probably know, the hadron cross-section or the proton-proton cross-section basically consists of sort of an elastic part and an inelastic part. The inelastic part and the total cross-section tends to grow gradually with center of mass energy. But I think the main point for us is that this cross-section tends to be on the order of, say, tens of millibarns. And it tends to there tends to be a simple dependence on the A of the material. So it goes like A to the 2/3. So we can define the hadronic interaction length, which is basically similar to the radiation length, but in this case for hadrons, it's basically the length after which we expect one nuclear interaction. And that hadronic interaction length should scale like A to the 1/3. Okay. So the hadronic interaction length is the thing that actually characterizes both the longitudinal and the transverse profile of hadronic showers. Okay. So how do they actually look? So you can see if you do, this was a simulation, I think. So this is showing for like a 250 GeV proton compared to a 250 GeV photon in air, how the shower will look. So you can see that in the case of the hadronic showers, they tend to be more spread out. And they tend to sometimes have an electromagnetic core with energy, but then energy also spread out at large transverse distances and over a larger longitudinal distance than for the EM case. Okay, so just a comparison of EM and hadronic showers. So I think if you look at the two things that govern the respective showers, so we said that the radiation length governs electromagnetic showers, the hadronic interaction length governs the hadronic showers. This ratio will actually grow as a function of A, as A to the 4/3. And you can see that there actually can be very different. So for example, for steel or iron, you can basically get a radiation length of about 1.7 centimeters compared to a hadronic interaction length of something like 17 centimeters. And you need about 6 to 9 hadronic interaction lengths to fully contain a hadronic shower. So this means that hadronic calorimeters need much more depth or need to be much longer than electromagnetic calorimeters. Okay. Yeah, and then this just shows that what I showed on the last slide, that this sort of hadronic interaction length as a function of Z. So as Z increases, the hadronic interaction length, this is per in this unit, grams per centimeter squared, it decreases slightly, but this radiation length decreases much more. Okay, and then this is how the longitudinal profile of a hadronic shower looks. So it's similar to the EM shower. except the governing scale is this hadronic interaction length. So as I said, you need something on the order of 6 to 9 hadronic interaction lengths to actually contain 95% of the shower. Okay, so I think for the lab, so Fred, I have I guess 10 more minutes.
Yeah, I think we can flex a bit.
Okay, great. So yeah, so I think, so now I wanted to talk a little bit about why hadronic calorimeters have much worse resolution than electromagnetic calorimeters in general. So the main thing, as I said, was you can have what's called this, you can have an electromagnetic component to your hadronic showers. So in particular, if you have a charged pion coming in, after its first nuclear interaction, you can produce a neutral pion, and that will go on and decay to photons, which will then create electromagnetic showers. So once a neutral pion is produced, all of its energy gets deposited via EM processes. And so it's basically a one-way street. Basically, once you produce it, you just get EM processes for this blue part. So FEM, so we can say we can define FEM as the fraction of the incident hadron's energy that's actually deposited via EM processes. Okay, so we can see two things. So first, we actually see that the average EM shower fraction for, say, incoming pions grows with energy. So as the pion energy increases, the fraction of the energy of that pion that's deposited through EM processes will increase on average. The second thing is that the responses due to the EM component and non-EM components will be different, okay? So what this plot shows is that if you think of the pion shower as composed of an EM part and a pi zero part or an EM part, which we call E here, this red part, and a non-pi zero part, this H part, the signal per energy deposited in the calorimeter, so the response of those components will be different for the pi zero part and the non-pi zero part. And most of the time, for most calorimeters, not for all, but for most hadronic calorimeters, this red part, this E part will be larger than H part. So this E over H ratio, when it's not 1, basically that means two things. So one, the fraction is changing, and also the responses are different for the two parts, the pi zero part and the non-pi zero part. So notice that the H tends to be lower, and this is due to this invisible energy that I mentioned, that some of the energy in the non-pi zero component is lost to this binding energy effect, or what we call the invisible energy. It's also wider, and that's due to the event by event fluctuations in the size of that invisible energy. Okay, so what we can actually define the pion response and compare it to the electron response. So if we basically subdivide this pion response into an electron, into an ENM part and a pi zero part, which is basically the fraction of the shower that's part of this pi zero part, times this E, which is the response for that EM part, and then you have a hadronic part. Okay, so the ratio of, say, a response of a calorimeter, a hadronic calorimeter, to an electron compared to a pion will be proportional to this E over H ratio times this thing here. So if your fraction of this EM fraction changes with energy, and E over H is not equal to 1, then this ratio will change with energy. Okay. Now, if you have E over H equal to 1, then E over pi will also be 1 on average. So we define two types of calorimeters. So one is called compensating, where E over H is equal to 1, and one which is called non-compensating, usually where it's undercompensating, where E over H is larger than 1. But you can also have overcompensating. E over H is less than 1. Okay, and the basic idea here is that since the fraction of the EM part of the shower is energy dependent, while E over H is basically mostly energy independent, the response of a non-compensating calorimeter will be nonlinear. And then it will be quite a challenge to actually extract the energy from a non-compensating calorimeter. It takes more work to do so. It's doable, but it's more challenging. Okay, so what about the non-EM response? So the non-EM part, we can write this H as composed of several components. So we can basically have a relativistic part. So that's basically the ionization loss of, say, pions, charged pions in the shower. There's ionization loss of protons. There's energy loss due to slow neutrons, and then there's this invisible energy part. So this hadronic response is composed of all these parts, and basically you have the fractions sum to 1. So so basically we can write this E over H ratio as composed of this E over MIP divided by this part. So we basically have this relativistic part, this slow proton part, and this neutron part. This invisible part won't contribute to the signal, of course. So what does this tell us? Well, we see that as we said, this EM fraction increases with energy, and then the hadronic part, the energy is the energy of the hadronic part of the shower is subdivided into different components. So into a hadronic part, into a slow neutron part, and into an invisible part. Okay, and basically the idea is that the response to this is of course 0, and then there's different responses for these three. So these three parts leave different signals. So in order to actually create a compensating calorimeter, what you would actually need to do is you would need to basically tune your response, your H response, in order to basically get the E over H ratio to equal 1. So there's a couple ways to basically do this. I'll just go through it very quickly. So one is that you use a high Z absorber, but then you use a hydrogenous active material, so something that contains a lot of hydrogen. And if your active material contains a lot of hydrogen, then you get elastic scattering of the soft neutrons that are produced off of protons. So you get a high energy transfer to the protons, and then a high specific energy loss for those protons. The second thing is you can tune the sampling fraction. So what you do here is that you actually reduce your performance to EM particles because you reduce the sampling fraction. But when you do that, you basically, by changing the sampling frequency, you actually tend to basically you reduce the EM performance, and you reduce how much your E response. So that actually can push you more towards compensation. So for example, in a lead scintillator setup, you can actually, if you have a 4-to-1 ratio of absorber to active material, you can get close to compensation if you have a hydrogenous active material. Okay, so then the other thing is you can change how much you integrate your signal over what time you integrate your signal over. And the longer you integrate your signal, you can get more of the neutron response. So the reason I went through that is there was one calorimeter, I call it, in the Zeus experiment in Hera in Germany, and they were the first compensating calorimeter. And what they actually did was they used depleted uranium interleaved with scintillator plates, and they actually achieved what's actually the best energy resolution for hadronic calorimeters, which was 35% over square root of E. And this is better than modern HCALs at the LHC, for example. And the initial idea here was actually to use fission energy. The idea was that the depleted uranium would actually fission, and it would release it would release some additional energy that compensates for the invisible energy losses. But, and while they actually did achieve compensation, it wasn't due to what the initial idea was. So the fission had nothing to do with it. And the uranium was actually not the most important aspect. What was actually really important was they did the three things I mentioned above. First, they had this hydrogenous active material scintillated with a lot of hydrogen. Then they had a tuned sampling fraction. So they tuned their sampling fraction to about 2%. And then they had an integration time of over 30 nanoseconds. So even though they had this small sampling fraction, which means that it had a degraded sampling resolution and degraded EMM response, and they had this large integration time, which means that you integrate more noise, the Zeus HCal still has the world leading record in hadronic energy resolution. So this shows that the importance of compensation for energy resolution is actually more important in general than these other issues such as sampling fraction or integration time. So the main driver of poor HCal resolution in general is what we can conclude is actually the invisible energy, which is produced in hadronic showers, which leads to non-compensation. So what do I mean by this? So basically what this is saying is that for hadronic showers, the sampling fluctuations only contribute a small amount to the total resolution of the hadronic showers. So that's what's shown by comparing these two curves. But the sampling fluctuations dominate the resolution for EM showers. So if you have an EM calorimeter, what really matters for your sampling calorimeter, what really matters is your sampling fluctuations. But for hadronic calorimeters, what really matters is how you're dealing with the invisible energy losses. So what are the two things that actually matter? So one is this fluctuations in this EM fraction, and one is this fluctuations in this invisible energy loss fraction. So the first part is what actually dominates for most non-compensating HCals, okay? And what we can see is that here, so this is showing that if we have a 150 GeV pion on a non-compensating or just on a hadronic calorimeter, this is the electromagnetic fraction for some amount of events. This is from some simulation. And what you can see is that there's this, first off, there's a large fluctuation. So event by event, you get a large change in the electromagnetic fraction. And you get a positive tail towards here. So there's an asymmetry in the distribution. And this asymmetry is basically caused by this leading particle effect, that if your first interaction creates a pi zero, you get a large tail towards basically high electromagnetic fraction. And what this shows is, basically, if you have non-compensation, since there's this huge fluctuation event by event at a fixed energy, and the responses, this E and H are different, this pi response is going to fluctuate significantly. So compensation would actually remove this effect because the fluctuations in this would not matter anymore. And also with pion compared to proton-induced showers, there's actually a difference in terms of the signal. So the pion showers tend to give a larger response than the proton showers.
That's 2 more minutes.
Okay, sure. And then I think the fluctuations in invisible energy, so that's the second component. So there can be significant fluctuations in this invisible energy event by event. But what's interesting is there's a strong correlation between the distribution of this invisible energy, so the size of this invisible energy for each event, and the number of neutrons produced. So efficient neutron detection gives a quantity that correlates with the invisible energy and thus reduces the impact of fluctuations. Okay, so then just the last two slides. So this is examples of some non-compensating HCal performance at the LHC. So this is basically for CMS, and this is for Atlas, and you can see some of the resolutions. And you can see that they tend to be worse than for the compensating calorimeter at Zeus. Okay, so this is resolution. So, yeah, and then realistic calorimeter systems really consist of both ECALs and HCALs. And particles would deposit energy in both. And it's a real challenge to intercalibrate these two different calorimeters because the ratio of the energy deposits in the two calorimeters is not equal to the ratio of the observed signal. So you have to use, so there's a variety of approaches to actually try and do this. And all of them have different advantages and different drawbacks. Okay, so let me just skip this. So yeah, to summarize, I'll just say, so calorimeters are widely used in particle physics. And as we see, there's a wide variety of calorimeter types to serve different situations. So while the underlying interactions between particles and matter are quite simple, the response of calorimeters, especially hadronic calorimeters, can be quite complex. And the future of calorimetry is based on one, integrating calorimeter response with that of other detectors. So this is called particle flow approaches to reconstruction, and also reducing the effects of hadronic shower fluctuations. So this is this idea of dual readout or triple readout calorimetry. So yeah, so that's all I had. So if there's any questions.
Yeah, thank you. So I remind you that this evening we have our discussion, 7:30. You can also pick up the linens before then. Why don't we take half an hour break and we'll start the next one at the 3:15. So you can break then, also catch Barack over coffee, and we'll see you in 30 minutes. Thanks.
Quick question. So, in these simulators, we're just looking at the energy from the scintillators, right?
So it's really we're counting the number of scintillating photons. So yeah, so it's basically as any particle has a scintillator, use enough photons, and that's basically count how many.
I would imagine that a fraction of those photons racked out or don't make their way into like PMCs or, you know, so how do we account that energy loss?
So it would depend. So we, as you said, we lose some fraction. In most of the cases, that fraction is constant as a function. So we get basically a proportional version. So one example is in so in CMS, for example, they have light time state. And you have to look at light time state itself. It produces around 200 photons. So if a particle deposits 200 MeV, it could produce, I'm sorry, 1 MeV will produce 200 photons.
And those photons come out radially, right? It's not.
Those photons, yeah, they come out radially, but some of them will be totally internally reflected, some will get lost. Sometimes you wrap it and you get some, yeah, but you'll lose a significant fraction. Now on the back of, and then you have, say, a photosensor. And that photosensor will also have some.
This is correct.
Perfect. So at CMS, they end up getting something like 10, I think something 10 photons per MeV.
So
That's. Even though you're losing fraction.
So if it comes
as long
with
as
color factor.
Yeah,
So suppose.
I mean, just a question then on your, your Poisson statistics then goes like square root of 1 over square root of 10, 1 over square root of 200.
Yeah.
You know.
Here.
Thank you very much.
Because yeah. We should large and see. It comes as you square root of calculations.
But that's what folks. Oh, because we work with other people that
DAT, that's just the president of the mental president operator CF.
Since when are you?
Trace of one.
Since when are you? You know,
Okay.
what are the talks?
And the plugins, so
Very
CF.
early, that's just early for.
Yeah.
I think it's like at 11:30.
Plugins, yeah.
I
Because
was
it's
alone.
and it's multiplied by an extra alpha s.
We had a great.
So we have alpha s from the now, without the.
You're good too. Yeah, I guess you didn't. Much, yeah.
It's proportional
Yeah,
to
that's-
C. So the relative
I
increase here, so this diagram brings an extra alpha s and CO. Compared to this. Okay. And that's it. Now we'll look at this diagram, right? This is color A, this is color B. Right? Still color sequence. It must have two blue ones, it's other alpha s. Okay? It has a color trace of TATB from going around the outer loop. And then inside the inner loop, you also have a trace of TATB. Right from this loop. And in principle, you can say, oh, this is my quark anti-quark, it can be any flavor. So in principle, if you sum of flavors, you can also have right, number of flavors. Okay, now what is this? This is 1/2 delta AB. This is 1/2 delta AB. Altogether, it's 1/4 delta AA, which is 1 plus the and C squared minus 1, right? Number of adjoint colors, which is approximately NCO. Okay, so this diagram holds. Yes. So we have alpha s squared and C squared and F over 4 together. We divide out this NC, right? That's 1 over NC. Then it becomes proportional to forget about factors, right? Becomes alpha s squared and C and then. Okay, so what is the legend C? And C goes to almost infinity, say large. Alpha s and C is fixed. That's Dooft's legend C limit.
Pero es que no está difícil.
So in that limit, this diagram is a
Nada más
constant
integrar.
contribution, right? So
Ya, ya.
alpha s and C is.
Una forma de integrarlo. Es lo que hay que ver. Ya te queda ahí la forma explícita de.
From there. This guy here is alpha s squared and C.
Es que la PT.
Forget about an F, right? We're just taking legend C limit.
Estudiar la PT.
Then this is alpha s times alpha s and C. And this goes to 0. Right? Because another way of saying, you can write this as alpha s and C everything squared over NC. So you have a constant squared divided by NC, and C goes to infinity, this goes to 0. Right? So therefore, this diagram is subleading at legend C. So the legend C limit. You can come up with other limits like legend C and an F limit. So this is a Dooft limit. Then there was Veneziano, who said, okay, let's do the large and C and an F limit. So NC goes to infinity, alpha s and C constant is fixed, but also NC over NF is fixed. Then it's kind of like what you